coefficient. Yes, we are at shortcut methods to find out particular solution. So let me revise the formula today. Tomorrow we'll see few solved examples on it. Okay, the first thing that you should know that in LDE, capital D, this capital D denotes d by dx operator, that is a differential operator, while 1 upon d indicates the integral operator. Okay, so whenever we come across d of some function, take a derivative, and when we take 1 upon d of some function, integrate it. Okay, now the formula for particular integral is yp is equal to 1 upon pi d of fx. Okay, so this equation is in the form pi d of y is equal to fx, then yp is this one, that is 1 upon pi d of fx. There are near about total 11 shortcut methods that we have for getting particular solution. Out of that, uh, we we just completed the first five. Okay, the first one is exponential function e raised to x. So whenever we come across e raised to x, replace d by a. Uh, okay, just we have to replace d by a in that phi of d, in this function of d, replace d by a. Now, when the base is a, that is exponential function with the base a raised to x, replace d by log a. Replace this d by log a. The last thing, when there is a constant, constant can be taken as a constant into e raised to 0 x. So replace d by 0. Replace d by 0. So that about the case 1, which is known as exponential function, e raised to x, a raised to x, or c. Next thing that we have is a trigonometric function, sin ax plus b or cos ax plus b. In some of the case, only sin ax is there or only cos ax is there. In such a case, we replace every d square by minus a square. Yes, remember, there is no replacement for d. D we have to keep as it is. Only d square we can replace it by minus a square. If the term of d cube is there, then we have to replace it by minus a square d, and d raised to 4 we replace by a raised to 4. So in short, replace only d square by minus a square and keep d as it is. Similar thing is in the hyperbolic function, sine hyperbolic x or cos hyperbolic x. Instead of d square by minus a square, we replace d square by plus a square. Okay, that is the change. We replace d square by plus a square. So that about a hyperbolic function. Remember, the maximum examples in exam are coming in exponential and trigonometric function. Rarely the hyperbolic example will come. Okay, there is one more important thing that we have. Let me come to that point, and that is when we replace uh, when we replace uh, when we replace here uh, d by a or d square by minus a square, in some of the case this phi of d coming 0. If this phi of d is becoming 0, in such a case you have to multiply by x. You can observe x is written before the operator, x is outside the operator, then differentiate the denominator, x into 1 upon phi dash d of fx. If that phi dash d is again 0, then again multiply by x, again differentiate the denominator. So we have to continue this process till the function of d becoming non-zero in the denominator. If it is 0, every time multiply by x in the outside and differentiate the denominator, and then replace either d by a or d square by minus a square, depending on whether it is a trigonometric function, exponential function, or hyperbolic function. So that about first three shortcut methods that we learned here. So yes, I will send 1 2 solved examples on these. So till then, bye. Thank you. Welcome all of you in the second video of linear differential equation with a constant coefficient. In this example, we are going to see the exponential function. The example is d minus 1 bracket cube of y is equal to e raised to x plus 2 raised to x minus 3 by 2. Yes, in exam you will not get all the three terms. Generally, you will get either only e raised to x or a raised to x, or sometimes e raised to x plus some constant, that one only. But yes, this example contains all the three possibilities of the exponential function. Okay, so in every example, we have that pi d of y is equal to, yes, pi d of y is equal to fx form. So equate function of d to the 0. So in this case, function of d is like d minus 1 bracket cube of y is equal to 0. So equate that to the 0 and find the roots. In this case, 1 is repeated thrice. Okay, remember, whenever the root is repeated, you have to write that number of times. It is a cubic equation, it should have three roots. So 1 is repeated, 1, 1, and again 1. So there are three roots. Okay, so for repeated root, we know the complementary function is written like this, like c1 plus c2x plus c3x square into e raised to x. So the number of constants appeared in the complementary function is equal to the order of differential equation. Right now it is a third order differential. Okay, so it have three constants, c1, c2, c3. All constant appears in complementary function only. There is no arbitrary constant appeared in a particular solution. Particular solution is a free from arbitrary constant. Okay. Now this step 2. So in step 2, yes, the formula for yp that we have is yp yp is equal to uh, yp is equal to 1 upon phi d, 1 upon pi d of fx. Okay, yp is equal to 1 upon pi d of fx. So in this case, this pi of d is d minus 1 bracket cube. So 1 upon d minus 1 bracket cube e raised to x. Now what I done, as there is a in RHS we have that three terms, e raised to x plus 2 raised to x minus 3 by 2. We are taking for e raised to x separately, 2 raised to x separately, minus 3 by 2 separately. So it denoted by yp1 plus yp2 plus yp3. So yes, whenever there is addition or subtraction, you can find out their particular solution separately also. So right now for e raised to x, yes, e raised to x we replace d by 1. So when we replace d by 1 in d minus 1 bracket cube, the denominator coming 0. So multiplied by x outside, and then the derivative of that d minus 1 bracket cube is a 3 times. This is 3 times d minus 1 bracket square into e raised to x. But again, when we replace d by 1, it is coming 0. So again multiplied by x, so it becomes x square, and the derivative of 3 times d minus 1 bracket square becomes 6 times d minus 1. And lastly, when we replace third time d by 1, then again it is becoming 0. So third time we again multiplied by x, and the derivative of that 6 into d minus 1 is only 6. So we get yp1 as x cube upon 6 into e raised to x. That about particular solution for e raised to x. Now let me come across 2 raised to x. For 2 raised to x, yes, it is very simple. Just replace d by log 2. So we got that as answer. So this is yp for 2 raised to x. And the yp3 now, the third, which is for the constant minus 3 by 2. So indirectly there is e raised to 0x is there, e raised to 0x. So replace d by 0. We replace this d by 0 and we got 3 by 2 as the answer. So lastly, don't forget to write this okay, complete solution as yc plus yp1 plus yp2 plus yp3. So that about the first example, case 1. Okay, so we'll stop here for the second example. Sorry, first example. Welcome all of you in the third recorded lecture, or I will say third recorded session. Okay, these are very short session of maximum 5 to 10 minutes only. Okay, so this is about the third session. So the example we are starting here as a type 2 trigonometric function. So the example is here, which is a d square plus 1 of y is equal to sine x into sine 2x. Now RHS should be only like RHS is in the form of multiplication, and that we should convert into the addition, and then only we can apply our shortcut methods. We'll see that in the YP. So step one is YC. For YC, yes, we equated pi d to the 0 and we get the root as plus or minus I only. So in this case, we have only imaginary root. Generally, we compare it with alpha plus or minus I beta. Okay, in this case, alpha is a 0, so that is a 0. So only it is plus or minus I beta. And whenever alpha plus or minus I beta is a root, we have YC as a e raised to alpha x C1 cos beta x plus plus C2 sine beta x. Okay, so in this case, yes, e raised to alpha, that is e raised to 0x, that is 1. So only C1 cos beta, beta is 1. So if you compare alpha plus or minus I beta with plus or minus I, beta is 1. So if beta is 1, C1 cos x plus C2 sin x, that will be our YC. So that is the end of the first part. Okay, so we completed the first part. Now come to the second part, which is a YP, particular solution. The formula for that is 1 upon pi d of fx. Yes, in this case, pi d is 1 upon pi d is like 1 upon d square plus 1, and RHS is sin x into sin 2x. So here we multiplied by 2 and divided by 2 so that we can use the formula for 2 sin a sin b. 2 sin a sin b formula is, yes, those who remember this, which is a trigonometric formula, 2 sin a sin b formula is cos of a minus b, cos of a minus b minus cos of a plus b. Okay, so by that formula we get this as a 1 by 2 as it is. 2 sin a sin b is a cos of a minus b, that is x minus 2x, minus cos of a plus b, that is x plus 2x. So cos of minus theta is a cos theta, so it becomes cos x only, and that is a cos 3x. Now yes, it is like that. We have to take separate particular solution for cos x and separate particular solution for cos 3x. So this 1 by 2 is taken outside. Okay, outside the operator. Constants, yes, we can take outside the operator. So 1 by 2 as it is. In the first case here, when we replace d square by minus a square, the denominator is coming 0. So multiplied by x, derivative of d square plus 1 is a 2d and cos x as it is. Okay, so next time this 1 by d is 1 by d is there. 1 by d is nothing but integration of cos x, and integration of cos x is a sin x. So x by 2 outside as it is. Okay, that about the first term. Now come to the second term, this one. For the second term, yes, if you replace d square by minus a square, means d square by minus 9. So it is not 0, so directly we got as answer, which is a 1 by 8 cos 3x. And at the end, yes, don't forget to write this every time. That is yc plus yp is the complete solution, and that about the trigonometric function. So in trigonometry, mainly we come across three possibilities in the denominator. First possibility is 0 in the denominator, that we observed in this term. When 0 comes, multiply by x, differentiate denominator and proceed for yp. Case 2, we get constant directly in the denominator. When we get constant in the denominator, we have that directly yp. And the third case is there, which is the linear term in the denominator. Yes, I will take next example on that, so that all the three possibilities of trigonometric function will be clear. Okay, so that's for this session. Thank you. Okay, welcome in the fourth recorded session. So in this session, we'll see one more example for a trigonometric function where the denominator comes the linear term when we calculate yp. So right now our example is like d square plus 2d plus 1 of y is equal to 4 sine 2x. Step 1, yc. So the factors minus 1 repeated. So when it is a repeated root, yes, obviously the yc will be c1 plus c2x into e raised to mx, and in this case m is a minus 1, so e raised to minus x. So that about the case 1, which is a yc. Now step 2, yp. So for yp we have 1 upon pi d of fx. So in this case, that phi d is a d square plus 2d plus 1 of 4 sine 2x. So when we replace d square by minus a square, so we are replacing d square by minus 4. You can observe only d square by minus 4. We cannot replace this d by anything. So we keep as it is. So it is a minus 4 plus 2d minus 4 plus 2d plus 1 should be in the denominator. So this plus 2d as it is, no replacement for it. So simplification is 1 upon 2d minus 3 4 sine 2x. So whenever there's a linear term in the denominator, the method says yes, we should rationalize. The rationalize means we will multiply by conjugate of the denominator, and the conjugate of the denominator is a for 2d minus 3, the conjugate it is a 2d plus 3. So we multiply and divided by that 2d plus 3. Okay, so when we multiply and divided by that 2d plus 3, so the numerator 2d plus 3 as it is, the denominator become 4d square minus 9, because this is a minus b into a plus b, so it is a square minus b square. And now we got that quadratic term in the denominator, and we replace that d square by minus a square. So we replace that d square by minus 4 here. Okay, so this 4 into 4, that become minus 16 minus 9 is a 25 in the denominator. This 4 is taken outside here, so minus 4 by 25, only 2d plus 3 remain as it is. So let me operate this 2d plus 3 on sine 2x. So 2d, just we are multiplying 2d into sine 2x plus 3 into sine 2x. So this thing we written here. Okay, and now 2 into d means the derivative. This is the derivative of sine 2x. Derivative of sine 2x is cos 2x, and this sine 2x as it is. And lastly, yes, yc plus yp. Yc plus yp is a complete solution. So the main thing is here where we come across the rationalization. Okay, so that about the new thing that you have. So that about a trigonometric function. Okay, and yes, one more example I will take on hyperbolic function, and then we'll see the theory of algebraic function. Okay, thank you. Welcome in the fifth session. Yes, so today we are going to see hyperbolic function. So let me see the example. The example is given as a solve d cube y by dx cube minus 4 dy by dx equal to 2 times cos hyperbolic 2x. Okay, so yes, this d cube y by dx cube is taken as a d cube, while dy by dx is taken as a d. So it becomes d cube minus 4d is equal to 0. So when we taken a d as a common, it becomes d into d square minus 4 equal to 0. So roots are 0 plus or minus 2. So there are three distinct roots. So we have yc as a c1 e raised to 0x plus c2 e raised to 2x plus c3 e raised to minus 2x. That about yc. Come to the step 2. Step 2 is a yp. Yes, common formula 1 upon pi d of fx. In this case, pi d is d cube minus 4d, and fx is a 2 times cos hyperbolic 2x. The method is now we replace d square by plus a square, d square by plus 4. So when we replace d square by plus 4, it becomes 4d minus 4d, that is denominator is coming 0. So yes, we have to multiply by x outside. Derivative of d cube is a 3d square. Derivative of minus 4d is a minus 4. So the derivative of entire the denominator is a 3d square minus 4 into 2 cos hyperbolic 2x as it is. Don't do anything with that. So keep x outside till end. Now we will replace d square by 4. So if we replace d square by 4, the denominator is not coming 0. Yes, we can replace them directly. So 3 into 4 minus 4 into 2 cos hyperbolic 2x, and the simplification gives us at the end yc plus yp as a complete solution. Okay, so this is a simple examples. This is required. Whatever the few examples given in the given you daily, so you should do at least 2-3 examples of each type. Yes, nothing is required more than that. Okay, so understanding is main thing. Okay, thank you. That about your hyperbolic function. Okay.